One application of matrix transformations is as a way to describe what are known as discrete dynamical systems or systems that change over time. For example, suppose we have a streaming company that has two subscription plans. We'll label the basic plan with a B and the premium plan with a P. And suppose this streaming company has 10,000 total subscribers. Each month, 80% of the basic users stay basic, while 20% upgrade to premium. 90% of the premium users stay premium, while 10% downgrade to basic. We're going to assume that no one leaves this streaming platform, that everybody stays on and either moves to basic or premium. And we're also going to assume that no one else joins. So we sort of have this closed ecosystem of customers for this streaming company. So we have these 10,000 customers, and they all remain customers, and no new customers are added, and they sort of move between basic or premium with the given percentages. So we can represent a vector x where we have the number of basic users as the sort of first component of that vector, and the number of premium users as the second component of that vector. So for example, if all 10,000 subscribers were basic, then we might use the notation x0 to represent that particular state of this system, which would include, 10,000 as its first component. Everyone is at that basic level, and 0 for the premium. What would happen after 1 month? So what is t of x0? We can, work that out using the previous information here. 80% of these users, since they're all basic, would stay basic, while 20% would upgrade to premium. So t of x0, t of this 10,000 0, would equal, well, so 80% of them, which would be 8,000 of them, would stay basic, while the other 20% would move to premium. So t of x0 in this case would be 8,000, 2,000. On the other hand, what if all 10,000 subscribers were on the premium model? What would the distribution in this case look like after 1 month? So t of 0, 10,000. Again, kind of going back to our rule, 90% of those users will stay premium, while 10% will downgrade. So we'd have 90% of them, or 9,000 of them, remain premium, and 10% or 1,000 move to the basic plan. So could we use those previous results to find the matrix A where t of x equals ax? Kind of similar to what we had been looking at earlier, all we need to know about a transformation is sort of what it does to two vectors, and then we can figure out, if we're choosing those two vectors wisely, then we can figure out this matrix A. And so 8,000, 2,000, I'll point out that 8,000, that this 10,000 0 vector is 10,000 times what we've called E1, 1, 0. And we know what happens to that 10,000 0 vector. And so t of 1, 0 is just going to be 1/10,000th of t of 10,000 0. So it's going to end up to just be 0.8, 0.2. If we take this 8,000, 2,000 vector that we found earlier and divide by 10,000, we'll get 0.8, 0.2. Similarly, t of 0, 1 is just going to be 0.1, 0.9. And so this transformation, t of x, will be defined by the matrix A, whose first column is 0.8, 0.2, and whose second column is 0.1, 0.9. And we take that and multiply it by the vector x. So suppose we had a different situation where we had 7,000 basic members and 3,000 premium members. What would happen after 1 month? So x1 would be A, that's that matrix we just found, 0 0.8, 0 0.2 is the first column, and 0 0.1, 0 0.9 as the second column, and we can multiply that by 7,000, 3,000. Now you could just do this directly where you sort of, know the rule and take those 7,000 basic members and sort of send 80% of them to basic and 20% to premium, and take those 3,000 premium members and do the 90% and 10% and figure out where you are. But this is a little bit easier, and we're going to see how using these matrices is going to simplify things even more as we move forward, and especially as we get to some topics later in the course. So we do this math here, and let's just see. So this computation, we would get, I think, 5,900 and 4,100. So after 1 month, if we started with 7,000 basic and 3,000 premium, and sort of follow the rule we laid out, this is where we would end up. What if we looked several steps ahead? So x1 we just discovered was that, and we're starting with that same 7,000, 3,000, was that 5,900 and 4,100. If we wanted to go one more step, x2, we would take A, that 0 0.8, 0 0.2, 0 0.1, 0.9, and multiply it by the vector 5,900, 4,100, where we are after 1 month. And so we do that math out. And just take a second and try this out yourself as well. And it looks like we got 5,130 basic users. And then the rest of them should be the premium users. So that's the other 4,870. And we can do the same thing, or the same kind of thing, for x3. Take our matrix and multiply it by the vector that we just found. So we do that out. Okay, and we end up with, it's like 4591 and 5409. So, you can see how you can kind of just keep going into the future here, assuming that those, those percentages don't change, that, that 80%, 20%, and 10%, 90% don't change month after month. You can sort of look far ahead into the future to, sort of see, where you predict the number of streamers would be. And this is obviously a much more simplified example than an actual streaming service would be dealing with. But you can hopefully see how this could be generalized to a little bit more complicated scenario. One thing to point out here is that, we saw we were going sort of from one step to the other by multiplying the previous vector by that matrix A. If we were to, kind of put that all together, x1 is A times x0, x2 is A times x1, but x1 was A times x0. So, this is really A times x0, which is A squared times x0. And same thing for x3. x3, we can maybe show some of this out, right? So x3 is A times x2, but x2 was A squared times x0. So this becomes A cubed times x0. Okay, so you can sort of generalize this, right, and move as many steps into the future as you'd like. For example, the matrix that moves the system forward 7 steps is, a to the 7th. The vector xk describing the system at time k is called the state vector. So here we're defining some terms that we were just using in that previous example. And the matrix transformation T of x equals ax is called the transition function. This is all related to this idea of a discrete dynamical system. So if we begin with state x0, and x1 is a times x0, x2 is a squared times x0, x3 is a q times x0, a system that evolves according to xk plus 1 is equal to axk is called a discrete dynamical system. Just to really drive this point home, if we wanted to know kind of the nth step, this would be a to the nth times x0.